Hi everyone, just want to let you know that I forgot to bring my document camera to the class today, so I have to, run another lecture, probably just record what I covered in the class just now for the people who rely on the videos because you guys are not coming to the class. Okay, this can be a little bit shorter than a 55-minute class because I'm not having interactions with, people in the classroom, just like a monologue. I expect this can be only 20 minutes or so. Okay. And the schedule for this week, if we just go to the website and look at the schedule, I'm going to cover models for digital design for hopefully, I don't know, two lectures and a half or 3 lectures. And we're going to have a quiz on Wednesday regarding C5 layers. So I'm going to give you a top view of the layout, and I will ask you to draw the cross-sectional view of the layers. And I think you guys will be ready for the homework assignment on Wednesday or maybe Friday. I probably will move this to Friday, depends on the progress. And this will be due on Wednesday next week and can be changed to Friday, depends on the progress. And then we will have memory for circuit design for next week, and some IC power consumption and IC yield, and maybe something about the project for the week after next week, all right? Okay, so the first thing I want to cover is called a Miller effect. We have seen an RC circuit like this. If I switch on this voltage source and have a capacitor over here and resistor here, although this looks a little bit different from the RC circuit I have used. Normally we have the resistor in the front, but just look at this circuit. If I switch this on from 0 to VDD, for example, and the capacitance of this capacitor is C, and we know the charges, delta Q or something, so Q equals to what? CV. And the way to remember this is Q is always on the top, and you have Charlie and Victor as a servant for the queen. Okay, so Q equals to CV, or you can say C equals to delta Q over V, or V equals to delta Q over C. And the capacitance of the capacitor is C, and the voltage change is VDD. So you are getting a Q, which is a charge change of the capacitor. If you have a different circuit, I'm pulling up the source on the left-hand side to VDD, and at the same time, I'm pulling this down to the ground on the other side of the plate. And this can be a different story. And the reason we want to model the digital circuit in this way is because if I'm looking at the NMOS, it does exactly the same thing. If I switch this on from 0 to VDD, and before I switch this on, the output terminal was VDD because that was a disconnect circuit for the NMOS channel as being put up to VDD. So initially this was charged to VDD because it's being put up to VDD. If I switch this on, it's going to be put down to the ground. So the point, the voltage here, will be changed from VDD to ground. At the same time, so when this is being switched on, this is being switched off. Okay, so exactly the same case as here. That's how we model this capacitor. And we are looking at this capacitor in this circuit. It's actually a parasitic capacitance between the gate and drain. And there's another parasitic capacitance from the gate and source as well. So we're going to talk about this really quick. So you know, if you have a circuit like this, it does pretty much the same thing as this model. Okay. So when you have a one source is pulling the voltage from 0 to VDD, and the other side is pulling VDD to ground, down to the ground. It's doing the same job, because whenever this is being put up to VDD, it's pushing the positive charges to the plate, and also when this is being put down to the ground, this is also drawing the positive charges to the ground. So actually, whenever this is dumping positive charges, it's actually pushing positive charges from the other side. And at the same time, the other voltage source is doing the same thing. So the delta Q is actually 2Q compared to this one. If this is Q, this will be 2Q. Because the two sources are doing the same job and doing the same efforts to, from this side, it's drawing twice as much as the charges compared to this one. It's also the same as this side as well. Because when this is drawing, it's drawing positive charges to the plate as well on the other side, being caused by this source. So anyway, this can be a little bit hard to imagine, but just keep in mind, if you have two sources are doing the same job, then you are going to have an effective Q, which is 2Q, right? So in that case, we are having 2Q equals to C. Now the capacitance has retreated as an effective capacitance. So we're going to talk about it really quick. C times VDD. So now the effective capacitance equals to 2Q over VDD. This is actually 2C. Same capacitor, but if you are taking consideration of the this kind of effect, which is called Miller effect, it's effectively 2C instead of C over here. So this circuit can be modeled as one C here, and then another C here. So there are two C's effectively instead of one C. And this can be critical because it's how you can understand when you are modeling the parasitic capacitance, why the Cox here is not a half Cox, but is Cox, right? So let's take a look at the NMOS. So it has the parasitic capacitance here and another parasitic capacitance over here as well. Let's just draw a terminal instead of a ground. This is called CGD. This is called CGS. As a gate to drain parasitic capacitance, this is a gate to source parasitic capacitance. So these capacitors are not added to the circuit manually. They are there, intrinsically, they are there already, because if you look at the cross-sectional view of the NMOS, it has a gate floating on the top and has a gate oxide underneath it. And here is the N plus, two N pluses. And so we are in the process of modeling this capacitor over here, right? When we are looking at the cross-sectional view of the NMOS, we can split this into two halves. So we can model this capacitor over here. See, here's a top plate, here's a bottom plate, and here's the two terminals. So this one can be modeled as this one. It's the same as the capacitor over here. So this capacitor here can be modeled as this one. And if we name, this is drain, this is source, this is gate. So this will be CGD, this is CGS. If the entire capacitor here is Cox, oxide capacitance, Cox, then this half will be a half Cox, and this is a half Cox as well, since it's symmetric. And if we look at this circuit again, if we have a capacitor as a C load, which is initially charged to VDD, and whenever this is being switched on, all these charges previously stored in the plate, negative charges on the other side, so these ones will be discharged through the channel and go to the ground. Right, so the voltage at this output will be switched off. Okay, so these two nodes are doing the same job as this circuit, which means the effective capacitance over here, physically, I understand this is cogs. Physically, this is cogs as well. But if you connect this gate into a step function like this, right, and this will be switched off at the same time, then the effective capacitance over here will be changed to something else. So it's going to be two half cogses, which means it's cogs instead of half cogs because of the Miller effect, right? So which means the effective CGD is actually cogs whenever you are having this signal being fed into the gate and this is being discharged at the same time. Okay, so that's the same concept. And it's not being affected. So this CGS is not being affected because it's always being tied to the ground normally. It's always being tied to the ground. It's not changing at all on the other side, which is going to be this circuit. It's not changing. Only one terminal is changing. It's only the original capacitance. Right? Second, the effective switching resistance of the NMOS or PMOS. Or CMOS, right? So it's going to be Rn or Rp at the channel resistance. For example, I have this circuit and the drain was initially charged up to VDD, and I just turn this gate on. So the current will be, or charges will be dumped to the ground through the channel. And if you look at the RV curve, here's VDS, here's IDS, and here's the IV curve. And when that, so originally it is being charged, it is being VDS is being biased at VDD. But however, because it's not switched on, so it's off actually. So the biasing point is right on the top or right on the x-axis because there's no current. But it's being biased at VDD, right? So start from here. And then whenever this is being turned on, you're getting current. And so the current will be dumped to the channel, to the ground through the channel. So the current will increase. Then move to the left. And just going to follow the IV curve and go back to the ground. Right? Because VDD, IDS, whenever it's being totally discharged, you get no current left because all the charges are being dumped to the ground through the channel. Okay, so through this procedure, there will be an effective resistance because this is not linear. You cannot, so the resistance of the channel is always changing if you're following this curve. But we can model this as Rn, which is a curve like this. So we get a delta. So that's delta IDS. That's delta IDS, and this is delta VDS. So VDS over IDS will be the resistance, right? So just do Rn equals to delta VDS over delta IDS. So what is delta VDS? Which is exactly VDD. The delta IDS will be the maximum current over here. We can directly use the square law equation, which we covered in logic and also in some other classes. You don't have to remember this for in this class. We just going to show you how we calculate the Rn. So use this one, and then VDD, which is the gate voltage, minus VTH, and you can get Rn. So for all the examples being used in this class are giving you Rn values. So you do not have to calculate by yourself. They're all provided to you guys. That's how you model Rn. Same concept for Rp, right? There will be Rp you want to use, but also Rp is also provided in a table as well. Right? And then let's look at, since we already know Rn and Rp, we are able to draw the resistive and capacitive switching MOSFET model. Complete resistive and capacitive switching starting from the gate, and here's the input capacitance, and here's the source. This is Rn, and this is C out N, which is literally cox, and this is C in N, which is something. Let's take a look at that. What is C in N? For this model, you got a mirror capacitor here, which is cox, and another one is a half cox. So the total C in is actually 2/3 of cox. And the reason the output is cox is because if you just look at these two terminals, because we just split this capacitor into two mirror capacitors, and for each of them is cox. So it's going to be cox and cox for each of them. Then you're getting C out as cox. Just look at the output terminal. You're going to have a cox over there, right? So we don't have a load capacitor here yet. If you have a load, you want to add a load to it as well. A load capacitance. So in parallel, so we can just directly add this C load to the C out. So here's a model for the NMOS. Right. And then let's look at the time delays. All right, so there's two signals, and all the concepts over here. If this is 90% of the amplitude, this is 10% amplitude, this is 50% amplitude, and we have all these same points, 90%, 10%, 50%. So if we draw the time delay over here, the time difference between this one, the 90%, 10%, at the rising edge, it's called TR, it's a rising time. For the falling time, it's called TF. So these ones for input only. Keep in mind, this is just for input. And for the output, 90%, 10%, there will be a time difference here as well. So this is called TLH. Right, always looking at the output when you are trying to determine if this is LH or HL. This means from low to high, the time delay is LH, TLH. And from here, it's called THL. Right, these are all these rising and falling times. And for these two signals, 50%, at 50% amplitude of these two signals, input and output. This is input. Right, 50%, 50%. Then this time difference between the input and output at 50% of the amplitude of each signal is called TPLH. The propagation delay from low to high at the output. So that's the rule to find out LH or HL, because you always look at the output. The output is going from low to high. That's why we define as TPLH. For here, also 50%, 50% is called TPHL. Always look at the output, because the output is going from high to low. That's why it's TPHL. And let's take a look at the example for this case. TPHL or TPLH, the R 0.7 RC, depends on what is R, what is C. For TPHL or TPLH, no P, TLH, these are 2.2 RC. So the conclusion, we just use the conclusions, and I don't think it's being derived from the textbook as well, but we derived this in circuit 1, so I don't want to do this again for this one as well. Just use a 10% instead of 50%. So P50 is page 50 of the CMOS book. Estimate the full time and the delay time as the output of the following circuit. So this can be found on page 320 of the CMOS book. It's 10 micron to 1 micron technology, and it's 50 femto for the C load from 0 to VDD for the input. And here's the table which covers all the parameters for the NMOS and PMOSes. Example size for 10 micron by 1 micron. And this is the size for the 30 micron by 1 micron. So for this specific NMOS, we can, so the book just lets you know the RN and RPs, right? Then Cox NP 17.5 femtofarad, and this is 52.5 femtofarad. And this table can be found on page 317 of the textbook. It's using the 1 micron technology for educational purpose, right? It's not fabricatable. So it's asking for the full time and delay times. The reason it's a falling time because this is the original charge at VDD. So whenever this is being switched on, the VDD or the charge is being purposely stored in the cap will be discharged through the channel to the ground. And if you want to find out the R and C's for these equations, we have to draw the model first. So for this circuit, the way to model it is we only look at the output, right? It's asking for the output. So we do not consider any Miller capacitors or anything as the input. So we just draw the second half of the model. So there will be Rn and there will be a switch to control the on and off of the circuit. And here's the C load, which is 50 femto. And this is Cox. Why is this Cox? Because this is C out, right? C out. So C out, it's just getting a Miller capacitor over here, which is Cox. This is Rn. Okay, so that's the entire RC circuit, and here's the output node. And I just use whatever, this or this, to find out all the delay times. So for the first one, for the full time, so it's going to be THL, right? THL equals 2.2 RC. So what is R and what is C? R will be 1.5K. What is C? C is Cox plus the load, which will be 17.5 femto plus 50 femto for the load. And just do the calculation, which is going to give you 220 picoseconds. And for the propagation delay, which is the time difference between the input and output at the 50% amplitude. It's called TPHL, which is 0.7 RC. It's going to be 0.7 times 1.5K times 17.5 femto plus 50 femto. So the result is 70 picoseconds. So what if this is a PMOS? What if it is a PMOS? So let's look at this model. Initially, ground. I have to switch this off to turn on the channel because you need a ground to turn on the channel. So whenever I turn this on, this voltage will be put up to VDD. So it's actually doing this. It's exactly the same effect as the one we just covered for NMOS. So you got two parasitic capacitors here as well. This is CGD, which is this for now, but whenever you are switching it, it becomes Cox instead of half Cox. Okay. And the size for this PMOS is also 10 to 1 micron, 10 micron to 1 micron. But the parameters being offered in the table is for a 30 micron over 1 micron PMOS. So in that case, it's the same length, no problem, but this is 3 times narrower. It's not that wide. So which means it's not that wide, then the resistance will be higher actually, because when you have a wider piece of metal, the resistance will be lower. But this is actually higher resistance, will be 3 times higher as this one. So RP here will be 1.5K times 3 will be 4.5K. And for the capacitance, since you are getting a smaller plate for the capacitance compared to the 30 micron one, so the capacitance will be Cox P 3 times lower, which is 50.5 femto over 3, which is 17.5 femto. And since we know these parameters, we just calculate for T, because this is from low to high, it's TLH, which is 2.2 RC, which is 2.2 times 4.5K times 17.5 plus 50. So this will give you 60 picoseconds. For the propagation delay, it will be 0.7 RC, which is 0.7 times 4.5K, and the same capacitance, which is 17.5 femto plus 50 femto. So the overall time delay for the propagation delay will be 210 picoseconds in the calculation. All right. And now we're going to see the last thing I'm going to cover, which is the pass gate and transmission gate. Just a model to give you guys some concept about what's going to happen for these transmission gates. Pass gate and the transmission gate. If I give you a circuit like this, there's VL. So definitely you don't need a 3 transmission pass gates. So if you only have a single NMOS or single PMOS, it's called a pass gate. If you have both NMOSes and PMOSes, it's going to form a transmission gate. But this is a pass gate, right? Yeah, this is being part to VD as well. All right, so just look at this part first. The question is, what is VL for this circuit, right? Just look at this part first. This is kind of similar to this. It's not similar, it's exactly the same to this, right? Remember, we don't ground it, just a terminal. So for this circuit, this NMOS is being self-biased. This is always being turned on and it's always operating in the saturation region. So when you are trying to pass VDD to here, you're only getting VDD minus VTH as a maximum. The reason is if you, whenever, so for example, there's a point, there's a switch here, right? You just close the switch, you're trying to turn it on. And at the same time, this is going to turn on the channel gradually. Take some very short time, but it still takes some time. And so the VDD, the charges will be dumped to this terminal, and it's going to charge up this terminal. So the voltage will start rising, right? Whenever it reaches this voltage, it cannot rise anymore. The reason is the channel will be closed, or the channel will be switched off after this voltage, because the gate voltage is VDD, so VGS, whenever it reaches this part, VGS will be VDD minus this, which is exactly VTH, right? So in order to turn on the channel, it has to be at least a VTH. But whenever this is trying to increase a little bit more, the channel will be switched off. We cannot increase anymore from this point. So that's the maximum voltage you can pass from one side of the NMOS to the other side. And so in this case, these two has the same voltage. You can consider these are gate drain connected. It's a diode connection for the NMOS. So the maximum voltage can be passed to this point will be VDD minus VTH, no problem. But however, for this case, it's a different situation. The reason is, compared to this case, you have the same gate and drain voltage, but here you got a higher gate voltage and a smaller drain voltage. And remember that when we are doing the sample whole circuit, in order to pass the entire voltage to the other side, we want to turn on the NMOS more, right? We want to turn on the gate more in order to pass more voltage from the drain to the source. But now, compare these two voltages, definitely the gate voltage is higher than the drain voltage. That's why you can actually pass the entire thing to here. So the voltage here will not be VDD minus 2 VTH, but it's going to be VDD minus VTH. It's the same voltage, which means the entire drain voltage can be passed to this point if you have a higher gate voltage. Okay, you want to verify this really quick? Let's take a look at this. Whenever you are calculating for VGS, for this case, it's going to be VDD minus this entire thing here, which will be VTH, right? It's still valid. You can still reach this point. And for the very last stage, it's the same concept, right? It's being biased at the same gate voltage, so you're getting the same voltage as the previous stage. But for another example, here's VL, here's a gate. So what is VL in this case? Is this VDD? However, the gate is not VDD because of the VTH drop. So the total voltage will be passed to here is only VDD minus VTH, right? So in that case, Vout cannot be higher than VDD minus VTH in this case. Because you just calculate for VGS. What is that VGS? It will be this one minus this one, which is exactly VTH, right? So in that case, it cannot be higher than this voltage because the NMOS will be switched off. So you are trying to pass the entire VDD to this point, we can only get VDD minus 2 VTH in this case. All right, hopefully this makes sense, and we'll cover more about the digital models on Wednesday and Friday. Okay, thanks for watching.